So let me just call your mind back a little bit because it's been some time since we looked at this. I want you to remember, we particularly covered two kinds of sequences and series. I want you to recall, if I gave you something like, say, well, let's start at something weird. Let's start at something like 3, 1, 5, 9, dot, dot, dot. Here's a sequence. It's a sequence because I'm not adding anything up. It's just a list of numbers in order. Here's a sequence, and you can see that between each of the numbers there is a common difference of 4, right? A common difference of 4. And so you add 4 every time. So what kind of sequence is this? Do you remember? It's an arithmetic. Very good. An arithmetic progression was that word that I gave to you, right? So AP. Similarly, I could come up with something like, let's do it this way. We'll start at the same spot. How about this, and then this, and then this? So I've given you extra terms. I only really need to give you 3, as we pointed out before. But I've given you extra terms just to make it a little more obvious. Here there is not a common difference. Instead, you have a common ratio. You're multiplying by a number each time. In this case, yeah, we call it a geometric progression because there is a common ratio. The common ratio in this case is -2. Okay. So what we decided was, or what we worked out was, that there are nice, neat ways to think about these. If you're like, oh, what's the sum? What's the series? If I take the first 1,000 of these or 1,000,000 of these, for an AP, do you remember? You pair up the terms. Oh, sorry, you pair up the first and last, the second and the second last, and so on. Everything's nice. With this one, do you remember what we had to do? If I said, okay, here's a sequence, right? If you multiply everything by that common ratio, right? So if I say, what did we say the common ratio was? -2. So if I multiply everything by that, then every term turns into the next term, right? So this -3 will turn into a 6, this will turn into a -12, this will turn into 24, and so on, okay? And because you can match up these terms, you can, again, find the sum of the series in quite a nice, neat way. But not all sequences and series are APs or GPs. In fact, one of the important examples I gave you was this guy. What's this guy again? This is the Fibonacci sequence, which is neither an AP nor a GP, but it's one of the first sequences you learn. It's quite easy to wrap your head around. And it's quite simple to come up with different sequences that are number things. Here is another one. And I think this actually appeared as again, one of the questions in that chapter. This is the sequence of square numbers, right? And there isn't a common difference, there isn't a common ratio. So how do you deal with these things when you don't have the nice, neat patterns that we established before, okay? We're gonna look for a different pattern. So the question I asked you to look at, and it might help if we actually write this down first, was this one. It was number 7, and it looked like this. What's this? 3 times 5, I think? Yep. Okay, so this is what they want us to add up. And it just looks weird. It's all kinds of weird, right? There's no common difference. There's no common ratio. So how are we going to deal with this thing? What we are aiming to do is to try and sense, all right, well, we used some tools before to sense the pattern here, right? We can do something similar to sense the pattern here if we can get something that will show us, oh yeah, you can pair these things up, or you can cancel these things out. It won't be exactly the same as these guys because it's not an AP, it's not a GP, but there are other things we can do. So I want to take the problem, or the strategies rather, that I suggested to you right in the first lesson to try and look at this thing, and there are no words in it, but it's just as problem-solvy and unfamiliar as that thing with, what was it, the guy with three children, and we had to try and work out their ages. Do you remember that? And the violin, right? So what kinds of things did we do there? Well, I think the first thing was we wanted to dissect the problem. Do you remember that? It just looks weird and imposing, so how can we break this down a little bit? Okay. What I want to notice is a problem like this is almost set up to be dissected because there's an unknown number of terms, but every term looks the same. Do Do you notice that? They all follow a pattern, which is the whole idea of this one and then this one and then this one. How do you get from one term to the next? What do you do to advance from one term to the next? Each one of those things on the denominators, by the way, we have language for this. Rather than saying things on the what are these things? They're factors in a product, right? So each one of these factors, we add 1 to it. We increase it by 1 and it turns into this. And then each of these factors, we increase it by 1, it turns into this. And you do it until such a time as you get to whichever value of k you like, the 100th or 1,000th or something like that. But because you're making each of the factors advance 1, right, the gap between the factors is always 2. Right? The next one will be 4 and 6. Then the next one will be 5 and 7, and so on. Which is why the kth term is k and k plus 2. Does that make sense? So what I want to do is just dissect it. Let's just look at this guy. Every single term is in this format. So how can I work out what's going on there? What makes this term this term? Okay. 1 over k plus 2. I want you to consider something like this. Okay. If I asked you to add these two fractions together, what would be the first thing that you do? You would go for a common denominator, wouldn't you? So you're like, I can't get these two fractions to talk to each other in thirds and fifths, so I will get them to be, well, in this case, in 15ths, right? So in long form, I would write this as 5 over 3 times 5. I know that you know what that is. You could just go straight there, but I'm trying to point something out here, right? And then this guy you would write as, what would you write that as? It'd be 6 over, again, 3 times 5. Okay? So what I'm noticing is, one of the primary reasons you get fractions which have like lots of things on the denominator, extra factors on the denominator, like this, is when you combine two fractions, right? If you were to add or subtract two fractions together, then you sort of have to do this by necessity. You multiply the denominators so that you get a common one, right? So if we think about this 1 over k plus 2, what kind of pair of fractions might this have come from? Now I don't know, so I'm just going to take a stab in the dark. This again is a classic problem-solving strategy. Just try something and see what happens, right? At the very least, you see this guy here? It came from fractions with those denominators, right? So why don't I try taking those guys, k and k plus 2. Here's a pair of fractions. It has those individual denominators. So when I put them together, maybe I'll get something that looks like that. Okay? So let's try it. When you add these two together, I guess I would say consider. Because I'm just trying to think this thing through and throw some things at the wall and see what sticks. Okay? But they're not just random, it's an educated guess. What are you going to get? The common denominator is going to be k times k plus 2. But what will this numerator become? The first one. K plus 2, right? Because that's what you multiply the top and bottom by. What about the second fraction? Be k. Okay, now when I have a look at this, this gets the denominator that I wanted, but I don't even need to go much further. Like in terms of simplifying this numerator, you can see I'm going to get 2k plus 2, which looks nothing really like this. Okay, 2k plus 2. All I'm supposed to have is a number up there, no k's or anything like that. The k's have crept up because I've multiplied those things. So how would I overcome that? Well, I added those fractions before. I added them, which is why this and this combine in this unfortunate way. But that's not the only thing I can do, right? If I don't want any k's on the top, do you see there's a k here and a k there? I can get them to actually cancel each other out, can't I? Instead of adding the fractions together, why don't I try subtracting? If I multiply, I do have this, but then when things are multiplied together, I don't have something that's much simpler than what I've already got, okay? Whereas if I have something that's added up or subtracted, you see this is added up and subtracted, so I'm hoping for something to cancel out. So I'm gonna write the subtraction instead. Let's try this. What is going to happen? Well, it's gonna be exactly the same thing, except with a minus sign instead of a plus sign. So I'm gonna get this. Okay. Now this doesn't seem like it's all that helpful just yet. But let's poke on it and play with it a little bit. On the numerator, the k's are going to cancel, so what will you be left with? 2. Okay. It's 2. I actually want 1, don't I? That's what I really want. So being that this is what I started with, if it turns into a 2 on the numerator, and I want it to be a 1, I'm just going to, it's an equation. I'm just going to divide both sides by 2. Does that make sense? And I'll get the thing that I want. So I'm going to divide this by 2. I guess I'll just stick a half at the front, and that will turn this into 1. Are you happy with that? Now, I want you to, again, call back to a couple weeks ago. Do you remember we spent a long time on factorizing? Do you remember that? And we said factorizing was useful because you can reveal the structure of an object if you know its factors, right? Well, I'm trying to do something a little bit in reverse. I'm trying to break up something which has been factorized into different kinds of pieces. Here's why. If I can state this as 2 pieces, not 1, but each of the pieces is simpler, and there's a subtraction here. Hopefully if I bring that to bear up here, some things will cancel out.